あ、でも、先生には、番号から。あ、中澤先生に。長澤先生には言ってないんだ。今、転送しました。
あ、はい、はい。
いました。
1時間半ですよね。1時間半時間がある。
そうですね。はい、
はい
90分でお願いします。
はい、90分。
はい。なので、始めたいと思います。今日は、講師のですね、中国の上海の復旦大学の永田先生に、お話をしてもらおうかな。分野が別に分野になると思います。よく聞いてですね、物理のラジオを出してくれるかなと思います。今、パソコンのマーク。永田先生、聞こえます？
聞こえますけど、ちょっと聞き取りづらいです。
はい。じゃあもうちょっとでかい声で。埼玉大学の理学部の物理の教員だった井上です。よろしくお願いします。
よろしくお願いします。
大学は3年ぐらい前に、 お伺いしたんですけれども、うちの学生と一緒に。で、その時
はい。
に、生さんも言われましたね。化け物の生その先生、今日ここにもいらっしゃいますけど、一緒にスタンダードの方にちょっと参加させていただきました。そうそうそう。じゃあ、この授業は2時半まで、日本時間で2時半。1時間で2時半までなんですけれども、実践のペースで構いませんので、90分間、もちろん80分でも構わないし、1時間プラス Q&A でも構いませんので、先生のペースでよろしくお願いします。ただ、この授業を終わった後にまた次の授業が、学生さんたちは控えている可能性があって、ご存知のように、この時期、大学の、期末試験に当たってますので、90分、2時半、日本時間で2時半か。2時半っていうところはちょっとよろしく、お守りいただけるとありがたいと思いますけれども、あと、のペースに回っております。じゃあ、セミナーの方、よろしくお願いできればと思います。はい、よろ
はい。
しくお願いします。
わかりました。えーっと、どうも、直田と申します。一応、日本語は喋れるんですけど、英語で、お願いしますということで、英語で、トークをしようと思います。で、途中質問があったら、いつでも、質問してください。マイクを使って。僕、今、あの、会場がどういう風なのか全く見えてないんで、どうなってるかわかんないですけど、マイクを使って、質問してくれれば、多分聞き取れると思うんです。いつでも質問してください。質問は、英語でも日本語でもどっちでもいいです。どっちでもいいんで、英語に自信がある人は英語で質問していいし、日本語で質問したい人は日本語で質問してくる。ということで、じゃあ始めようと思います。Okay, so let's get started. So the title of my talk is the unreasonable effectiveness of mathematics in physics. Um, this one, sorry. Oh, yeah. So this one is, of course, the title is motivated by the famous quote, famous, how to say, the article by Eugene Wigner, who got a Nobel Prize, saying that the mathematics is the unreasonably effective in natural science. And this article is and also this title of this article is very famous. And then the end of the article, so he noted that we should be grateful for it and then hope that it will remain valid in future research and then that it will extend for better or for worse to our pleasure, even though perhaps to a bafflement to wider branches of learning. Okay. Yeah, so sorry. So I think I should mention that the sorry, the miracle of appropriateness of language and mathematics for formulation of the role of physics is a wonderful gift we neither understand nor deserve. Okay, and we should be grateful for it and hope it will remain valid in future research. So in this talk, I would like to explain how mathematics plays a role to describe the nature in simple setting, like in classical mechanics, electromagnetism, quantum mechanics, and special relativity, and then general relativity. All those topics, if you are like a physics student, you will learn, and then even math student, I think you will encounter. So during this talk, I will introduce through these topics, I will introduce something like a linear algebra, the algebra, and also Fourier expansion and so on. or like a Riemannian geometry, or like some group theory and so on. So which are very relevant to even math students. Even for the students who are outside of like physics and math, like for instance chemistry or biology, even like I hope you guys can enjoy the my talk by just like by touch like listen to those like the physical theory that discover nature. Okay. And feel free to ask questions during the talk. And so this is the content of my talk. Okay, let's begin with the classical mechanics. Any questions? So let us consider the very simple system. You have a n masses. Sorry, I think could you? There is some echo of my voice. I hope. Okay. Anyway, so there's the n masses. They are how to say coupled by springs. So these are springs. It's called harmonic oscillator. And then we like to understand the motion of this system. So n mass is coupled by string. And by Newton's law, if you Newton's equation, if you write the Newton's equation, m times this x double dot, this is the acceleration. Double dot means the second derivative of time. Okay, is equal to how to say the displacement of the xj minus xj plus 1 minus xj is just the distance between them. So if you just stretch a little bit this spring, you have attraction force. If you just push them together, so you have a repulsion forces. So those forces are given in here, and which can be summarized minus k times 2xj minus xj plus 1 minus xj minus 1. Okay? So there is a n equation for each masses. Okay? And if you just write down the position, so position of masses simultaneously as a vector like this way. Okay? This Newton's equation can be written like in terms of n by n matrix. A written here. So diagonal element is 2, and the off diagonal element is minus 1, and the other elements are 0. So we would like to solve this Newton's equation. To solve this Newton's equation, we would like to diagonalize. So we just diagonalize to this matrix. So namely, so we just multiply U inverse, which is some diagonal element. That is called diagonal procedure. And this diagonalization and so on is essentially finding eigenvectors and eigenvalues. So essentially amounts to the A times B is equal to lambda B. So B is called eigenvector and lambda is called eigenvalue. As you already noticed, I already put some Japanese terminology, but you can just learn the translation to Japanese. But I'm not going to use Japanese in this talk, but just you can just take a look. And we just do the simple assumption. This eigenvector has kind of like a sine wave, like form. So this is the assumption we would take. And this sine, the reason why I just picked this assumption is that this sine function, you know sine function, right? So you have sine function, x sine of x is something like this way, this sine wave. Okay. So this sine function satisfies this form, this equation. Okay. This equation. If you use this equation, you will notice that if you multiply A times B, so Bj is equal to sine times J phi. So A is essentially -1, 2, -1. Okay, so if you multiply B1, B2, B3, and so on, you just get the -1 J -1 element, J +1 element, and then the middle element is 2 times sine J. Okay? And then if there's the identity using this one, you will get that 2 minus 2 cosine phi times and the sine J phi. So you can easily see that this one, so Vj, so this is the eigenvalue, and then this B is the eigenvector. But you have to be careful that so here you have there's a boundary condition, okay? X0 and then xn plus 1 is fixed to be 0. Okay, it doesn't move, okay? This xj is just displacement, so therefore they do not move. So you need to impose a boundary condition. So the x0 is 0, so that the b0 has to be 0, and the bn plus 1 has to be 0, okay? So you multiply n plus 1, phi is equal to 0, which means that the phi should take pi over n plus 1 times some integer. Namely, so that the sine wave should, so it just starts with here, and the sine wave is move like this way. That's what it means. Okay. So therefore, so somehow the phi cannot be the arbitrary value because of boundary condition, and then the result of imposing boundary condition, you get the eigenvector as a sine times pi a over n plus 1 n times j. Okay, and then eigenvalue is just if you substitute this one and then use some identity in trigonometric function, you get this value. Okay, so when a is equal to 1, it becomes like this way. This is called lowest mode. Okay, it becomes like this way. A equal to 2, you have a oscillation, a little bit slight oscillation. A equals 3, so there is a 0 in middle. A equals 3, you have a 0 in the, there are two zeros in the middle, and so on. And as you can easily imagine, A equal to 4, you have something like this way. There is 3 0 in the middle, and so on. So these are called normal mode. And then if you use this eigenvalue and eigenvector, one can solve this Newton's equation very easily. Because if you substitute B double dot is equal to minus K over M eigenvector and B. Okay, so therefore this is very simple to solve it. And then if you solve it, you know that the time dependence is given by cosine times omega t, where omega t is called frequency. It's just k over m times this eigenvalue, and then take a square root. There's some still echo of my voice. I hope you can adjust your a position of your laptop or switch off your microphone. Anyway. Yeah, pretty sure. Anyway. So that's the way you solve this Newton's equation.
Mm-hmm.
Is it okay? Anyway, and the general solution to this equation is indeed the superposition of these various a. So a is equal to 1 to n and some coefficient. Since this differential equation or Newton's equation is linear, so you can, if you find multiple solutions, you can add them up with suitable weight. Okay? That is called linear combination or superposition. So each A are solution of the Newton's equation, And since the equation linear, you can add them up. And this is the solution. So this is the eigenvalue, and then time dependence is given here with the frequency omega. And then, so this general solution with this normal mode is summation. This is called, indeed, takes a form of discrete Fourier transformation. So once you have this system of this Newton's equation, indeed, you can relate the solution as a discrete Fourier transformation. And each normal mode is in this coefficient is called Fourier mode. And then we consider finite n, but if you take the lot of masses, so you have an infinite many masses, this system of the spring coupled by spring behave like an entire how to say entire, like the chain becomes strings, and the equation, this discretized equation become continuous. And that is called then the wave function becomes the Newton's equation becomes Newton's equation. As you can easily see, so here you have a second derivative of time, but here you can see so displacement of the two adjacent the masses. You have a displacement. This is kind of like a first derivative, and if you take the difference, further difference between them, you become second derivative in continuous limit. So therefore, so this discrete Newton's equation becomes the wave equation in the continuous limit, namely in n goes to infinity. And if you try to solve this wave function, you need to use the solution. It's very beautifully explained so-called Fourier series. Okay? And then in your in your coursework, most likely you have to take like a 数理物理 or mathematical method in physics. Or if you're a math student, you definitely learn some functional analysis and so on. You learn Fourier series. So, but I mean, the original motivation to study the Fourier series is to solve wave equation or this kind of like a Newton's equation for n masses connected by strings. Okay, so that's the motivation to study the Fourier. Indeed, Fourier is the person who lived around how to say the late 18th century to the beginning of 19th century, and then he had a very interesting career during the in his life. For instance, he had some like a political position with the Napoleon. And his interesting how to say, life is written in this very nice book for free analysis. So I highly recommend if you have if you're interested in. Okay, so that's a first connection between classical mechanics and then Fourier expansion. Any question at this moment? If not, I will move on to electromagnetism. So electromagnetism is the study of the the object with electricity or magnetism. Okay, and those study has been, I mean, vigorously done in the 19th century. Many brilliant mind has involved for instance the Gauss or like Biot-Savart or Faraday, Ampere, and then the final form of this the electromagnetism is given by Maxwell. Okay? And then those so this E is called electric field, and B is called magnetic field, and then rho is the electric density, and then J is a so-called electric current. So, so those four equations indeed describe the 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 physics of electromagnetism. And then these four equations called Maxwell equation. Even though each equation is first how to say discovered or described by different person, but the entire how to say physics of electromagnetism is the first given by Maxwell, and then these four equations but first how to say formulation by Maxwell is very complicated. There are so many equations. Like I heard like more than 10 equations to describe the electromagnetism. But these four equations, famous four equations given by HiSEP later. And I will explain one by one what it means for those equations. And then indeed, if you solve this equation, indeed you get the so-called, if you combine this equation and this equation, you get the so-called wave equation. And whose from which you can get the speed of light. And Maxwell already knew from this equation that the speed of light is 3 times 10 to the 8 meter per second. Okay, so 1 second you can just speed of light can travel like 7.5 round of the Earth. So that's the speed of light. And then this light is indeed described by the electromagnetic wave. So for instance, you can see my face, even though I'm at in Shanghai while you're in Saitama, because here there's a light hitting on my face and go to my laptop, and this laptop send to the signal to the computer in Saitama University, and that from this computer you get the signal from the slide, and that slide will just emit the photon or electromagnetic wave, and you can see hits your eye. So that the reason why you can see my face or even this slide is due to this electromagnetism. Everything. So although the behavior of photon or electromagnetic classically described by a light is described as these four equations. So which is formulated around the mid 19th century. So it's a very important equation, and then so I'll explain one by one. So that's why you need to learn electromagnetism. So I try to motivate you why you have to learn these subjects. So let's first consider this guy. So Gauss's equation. So this is the divergent of this electron field is equal to electron density. Okay? So to understand this meaning, so if you have a electron or positron, whatever, or a proton, so the charged object is somehow described by this electrical density. And then, so here in this case, you have some localized, charged object in here, but outside there is not can be understood as some vacuum. If you have a charged object, it emits so-called electric field. Okay? Electric field E. Okay, so this is a vector field, electric field, and you can see this line as which represent electric field. And in fact, you can apply so-called Stokes theorem. Okay? Stokes theorem is you can just, if you integrate the left-hand side of Gauss' law to the region B is, say like this, region B, and then since there's a derivative here, so this is the divergent. I forgot how you said. This is derivative. Essentially, this is del Ex plus del Ey
del y plus del EZ del Z is equal to blah blah. If you have a derivative and the integral inside the integral, one can just get rid of derivatives and it just remain this how to say, the surface integral. So this is the surface of this volume B. Okay? And you just integrate out this E like this way. Okay. So which means that and this is equal to, I forgot to mention, write down, this is equal to this is equal to del B rho of epsilon 0, which is total charge Q. So here I use Gauss's law. So that if you just integrate of entire charges inside of B, you get the entire charge Q. And in fact, this charge Q can be measured by just integrate out by the electric field along this surface. Okay. And indeed, this choice, so that you have a surface and you just consider electric flux. You just count the electric flux, how much electric flux you will get. Okay, so that's the right-hand side meaning. Okay, so therefore, you don't need to know about what's inside. Okay, what's inside? You just know about the electric field on the surface. Okay, on the surface. And integrate all those electric field along the surface, you know what's happening, how much charge you have inside the surface. That's the meaning of Gauss's law. And then what's more important is that so therefore, and as you know, so this surface is just sphere, okay, in a sphere. And if you just go to the how to say, the radius of sphere becomes large, the area of the sphere becomes bigger. Okay, so bigger. So therefore, so if you become a bigger sphere, the electric field become weaker. Okay? Otherwise, I mean, the charge conservation does not hold. Okay? So therefore, the electric field is inversely proportional to the area of this sphere. Okay? Area of sphere. So therefore, electric field is proportional to the area of sphere, which is proportional, which is 4 pi r square. So therefore, 4 pi r square is denominator. And if you integrate out over the sphere, you get the total charge Q. So that's how you get the electric field if you have a point charge in the origin. Okay. And this Stokes theorem tells us that this even though you just change this surface in like this way, the net after integration you get the same number Q. Okay, so therefore the deformation of the volume B does not matter. Okay, so deforming this the surface doesn't matter to get the entire charge Q. Okay, so that's the magic of Stokes theorem. Any question at this moment? And then how about magnetism? The magnetic field, you just have this equation. So this means that there's so here in the previously you have is equal to rho over epsilon 0. So this is the electric density, but here right hand side is equal to 0. So this means that if you have this always have this magnetic field has the how to say never begin and end. So because of the 0. This means that so once you have the same logic can apply. So once you have the whatever surface you have, surface like this one, integrate off the del B, and then this will give you B, and then this is surface B, this is which has to be 0. So net charges inside the sphere has to be equal to 0, because I mean you have a south pole and northern pole, and this is say this is plus and minus, and net charge has to be 0. And even if you, as you know, if you split the magnet, you just have a S N Sn. Okay, you always have net charge zero. Right? Okay, so the second Maxwell equation will tell us that the net magnetic charge has to be zero. Okay, but if you look at this equation and use this the vector equation, so del dot del cross is always equal to zero. So therefore, magnetic field B can be always written in terms of how to say X-ray product will so-called A, which is called vector potential. So A is vector potential. And because of this equation, you can always have you can always write down the magnetic field with vector potential with the exterior derivative like this way. Okay? And this A is the choice of A is not unique. You can always have a total derivative correction, which is called gauge free degree of freedom. Okay, and because of that, sometimes so this how to say theory of this electromagnetism is called gauge theory. Okay, later people call gauge theory. And this A is somehow doesn't look like, so we know that this, we can see this, how to say, vector field B, like if you put the, how to say, for instance, if you put the sand, and if you put the sand here and like 砂を置いて、ここに磁石を置くとなんかこういう magnet, you can see the magnetic field like this, indeed. But this B look like a physical field, but this A look like somehow like mathematically introduced due to this equation. Is it real physics? Does it have a real physics or not? And indeed, this A is indeed more intrinsic, have an intrinsic physical meaning. So the first person who made a brilliant use of this, how to say, gauge field A or vector potential is in the Paul Dirac. You might have heard of his name. He's one of the founder of the quantum mechanics or quantum field theory. Actually, he's a father of quantum field theory. 量子力学. He considered the following thing. So if you have the gauge field, it's like the gauge field, it takes the following form. Okay, theta. So the theta is the so-called. It's called polar coordinate. So if you have a sphere, so let's consider sphere, two sphere, and then so this direction is theta direction. It's polar coordinate, and this direction phi. Okay, and then r direction is this r direction, so radial direction. And then, so if you consider such a the vector potential configuration, such a function, okay, and then AN is the northern hemisphere, so the upper hemisphere takes the minus and the plus sign. In the southern hemisphere vector potential is the minus and the plus. If you take such a form, of course, there is something this discrepancy you can see in this equator. It's a gray circle. 赤道ではこうコンフィギュレーションが合わない because of this the sign difference. But this configuration difference can be how to say gauged away by this transformation. As I mentioned, this choice of vector potential is not unique due to this wonderful property that the del dot del chi is equal to 0. So therefore, you can always do the gauge transformation, and you can discrepancy between in the equator can be gauged away by this choice. Okay, and if you apply this equation del is equal to b, you can have a unique b. Okay, and if you integrate out over the sphere, so there's a magnetic field, you can see the just penetrate transversely on a sphere, and if you integrate out, you get a non-trivial. So if you do B over this S2, you get a non-trivial answer G, indeed. So you get a non-trivial G. So I have written here. So if you consider such a vector potential, you get a magnetic field which penetrates S2 will give you non-trivial magnetic charges. So therefore, it's called magnetic monopole, which has not been observed yet. But if you consider mathematically, mathematical theory of if you solve the Dirac equation, this is a natural consequence of this. Well, that's what Dirac proposed in 1930. And in fact, this configuration is so-called, can be naturally interpreted, so-called circle bundle over S2. You know the two sphere is easy to draw, which is written here, or here, even though my drawing is horrible. But you can also imagine three spheres. Three spheres that you can easily imagine that the, let me write down. Okay, maybe. So x squared plus y squared plus z squared is equal to 1 is two sphere. Give it two sphere. But the x squared plus y squared plus z squared plus w squared is equal to 1 is three sphere. Okay? This three sphere is indeed can be understood as a so-called circle figuration over S2. What it means. So you consider the, what does it mean? Two sphere. Okay? At each point, you have a S1. Circle S1. Okay, S2. And it's not just product. And then, so the product, if you consider product, you have just something like this way. But this S3 is certainly not the product of S1 and S2. It's 直積とか日本語で言いますけど。For instance, if you look at this equator here, and equator circle, equator 赤道は S1. S1 cross S1 is become like the surface of donuts. Okay, this is S1 is this guy. This S1 is this guy. Okay, so it's called torus. It's called torus, T2. People like T2. Okay. So if you just consider northern part hemisphere and southern hemisphere and try to glue them together by multiplying S1, when you glue them together, you have to do something non-trivial thing. Okay? So you just have this circle is glued by, when you glue them together, you just twist by one times into this meridian. It's called meridian, this circle. It's twist by this one. And then glue them together, these two torus. What you end up with this S3. Okay. So this S3 is indeed can be understood as a so-called S1 bundle over S2. And the equator, you just need to twist. This twist is very closely related to this gauge transformation we do in this equator. And in fact, so this twist is somehow captured by so-called per-Chern number, which is exactly what Dirac did. So you just integrate by S2 over this magnetic field. This F is indeed magnetic field, and which is given, is called mathematical called first Chern number. And this is the mathematical formulation of Dirac monopole, which is given indeed by Chern in 1946. But he's a very famous Chinese mathematician. Okay. So the theory of the Dirac monopole is indeed the mathematical structure of Dirac monopole is given in as a so-called it's called S1 bundle, U1 bundle over S2, and it's Chern class. So therefore, so this is one connection between the electromagnetism and then geometry or topology. Let's look at the fourth equation of the Maxwell equation. So fourth equation means what? So if you have a current, you will get a magnetic field. Okay? Let's consider current is circling around, electric current. 電流がこう流れてると思う。電流がこう流れたと思う。So then if you have a current in here, you have a magnetic field is generated by like this way. The B is like this way. So this Ampere's law tells us that if you have a current, it will generate a magnetic field. 磁場ができます。And you can get this if you just do the integral of this equation. You can obtain the magnetic field which is given here. So R2 is a position of R2 is a position here. R is the around here. R is here, and how much magnetic field you can get at the position R is given by this integration formula. You just need to integrate over C2 because you have a current in here. Okay? And suppose you have a magnetic monopole here, and just move around here, move around this another cycle C. Okay. So this, since you have a magnetic monopole magnetic field, so therefore you need to move around the magnetic monopole around the C1, you need the energy. And total energy can be just obtained by just multiply this monopole charges here, the unit monopole charge here, and just integrate out over C1, which is given here. Miraculously, the genius Gauss has found that this integral is always integer. And the which is now called a linking number. So for instance, if you have the integral out over here, okay, over here, you get the 1. You get the 1. Integer 1. Whereas if you have a current here, and the integral of C1, you get 0. And in fact, if you do the C1 is something like or in exotic configuration, something like this one. C1 is something like, and go back to here. This is C1, it becomes linking number is 2. Okay. And what's more interesting is that even though you change this configuration slightly like this, deformed this configuration C1, this integral do not change. The integral of this one is always equal to 1. Okay? So this is something called topology. Even though you deform the configuration without changing the topology, you always get the 1. So therefore, this linking number is called topological invariant. And it's called linking number. So Gauss, 1833, which made a great contribution of the theory of electromagnetism, already write the 1833 of this integral, exactly given here, which is always integer. It's a very magical. And then this linking number and so on will be generalized immensely in later part of the 20th century by Witten, but I'm not going to explain. Any question at this moment? So we saw the electromagnetism and then its relation to something called topology or like something called fiber bundle geometry, a chunk math. So those are the math hidden behind the electromagnetism. Any question at this moment? Feel free. If you have a question, just use a microphone and ask a question. Either Japanese and English is okay. If not, I'm gonna move on to quantum mechanics. I want to explain something interesting experiment, so-called Stern-Gerlach experiment. So if you have the Siba atom, through the non-uniform magnetic field, something like a something miraculous happened. So, sorry, I think I should have. So you have a spin 1/2. Sorry, something miraculous happened. So it's called. So you know that the angular momentum. For instance, if you look at for instance, how to say, the skating, like it used to be very famous Japanese skater, Hanyu Yuzuru. There's something called triple axel and so on. They just rotate, and then that, because they can, how to say, jump like that way without rotation due to angular momentum. In classical mechanics, this angular momentum becomes continuous, and it's given by the formula something like a J is equal to x times extra multiple of P. Okay, x is the position, P is the momentum, and this is it's called angular momentum. 角運動量. So classically, this it's continuous, but quantum mechanics, it's a microscopic world. It becomes discontinuous. And indeed, in this experiment, you only have an even spin up scale by h bar. It's called Planck constant. Spin up or spin minus. It becomes discrete. And either you can have plus 1/2 or minus 1/2 in the unit of h bar. This is called Planck constant. It's very, I don't remember the number. It doesn't matter, but it's just, if you have a h bar, which means you have a small world, quantum mechanics. It's microscopic world. Okay, spin is quantized by plus minus 1/2. And then if you have something, a magnetic field in Z direction, you can either have you can just, if you try to measure, okay, x, y, z is the axis x in three-dimensional space-time, z and y, okay, and then if you want to understand this, you just put some how to say, spin 1/2 particle here and try to measure the spin on z-axis. Okay, spin on z-axis means that if you have a z-axis and the spin is something like either rotating like this way or rotating like this way, either. Okay, you have a particle here, and if you have a rotation here, you have a spin up configuration, or if you have a particle here, and if you rotate like this way, you have a spin down configuration in z-axis. And we want to measure this. We want to measure the z-axis rotation. Suppose this particle have a spin up. This plus means spin up configuration. And next, we want to compare. We want to measure the spin in x direction. X direction is here, okay, in three-dimensional space. Okay. So indeed, if you try to measure the spin in x direction, in fact, spin x plus and x minus, the probability to measure the spin up in x direction, spin down in x direction is in 50% and 50%, as you can easily imagine. Okay, and then suppose you pick only, so you only pick x plus direction, and then throw away x minus direction, spin down direction. You throw away this particle and just pick only spin plus direction. Okay, and again try to measure the spin z direction in the spin. And then the first you pick spin plus direction in z, and next spin plus direction in x, you might think the next z direction, of course, Z plus spin up direction because we pick originally Z plus direction. Okay, but that's not the case. Indeed, again, if you in quantum world, if you try to measure spin Z direction, in fact, the spin up direction measurement would be 50%, spin down direction measurement is 50%. There's a 50% chance to get the spin down configuration. So therefore, it's a quantum mechanics. It's somehow the ordinary intuition in the ordinary life cannot be applied. So then, in quantum mechanics, everything becomes somewhat like behave quantum mechanically. And to describe this quantum mechanical feature, you really need to use linear algebra. And in fact, this linear algebra, indeed, so to understand the quantum mechanics, you really need to understand linear algebra. And then to describe this spin 1/2 system, you really need a 2x2 matrix and then the 2-entry vector. Let's describe a spin up configuration Z. This is Z plus, and the Z minus is 1, 0 and 0, 1 in 2, 0 entry vectors. And then let's consider the observable of the spin, which is that it is given by 2x2 matrix, sigma x, sigma y, sigma z. And then this matrix is very famously called the Pauli matrices, and we just scale by h by 1/2. Okay? And then this observable is indeed the quantity that will give you the spin measurement. And for instance, the eigenvalue of this observable is the outcome of the measurement, indeed. So for instance, if you want to consider the Z spin, you just need to consider the eigenvalue of this matrix. Okay, so this is really linear algebra for 2x2 matrix, and then this Pauli matrix or scale by 1/2 is satisfy this commutation relation. And this commutation relation is so-called SU2 Lie algebra, okay? Which for math student, eventually you need to learn Lie group and Lie algebra, and then this in quantum mechanics, not in quantum mechanics. So this commutation relation is naturally appears. Okay. If I heard the math student, so Lie algebra is indeed some vector space with this commutation relation is a multiplication. Algebra means addition and multiplication, and this multiplication is given by this commutation relation. Okay. So somehow, to describe this spin in quantum mechanics world, we need to use this 2x2 matrix, and then everything is determined by so-called expectation value. And then, oh, sorry, I think, okay, yeah. And then this spin is described by this vector with 2 entries, and then speed up configuration is 1, 0 and 0, 1. In general, configuration is given here. Spin directed to this n unit vector in n in 2-sphere direction is given here. Again, theta direction is here, phi direction is here. In general, this 2-entry vector is given here. Okay. So those are states that describe this spin that pointing to this unit vector here. In quantum mechanics, this state can be just scaled by complex number, like some sine of chi plus I times cosine chi, which is equal to, opposite, chi plus I sine chi, which is e to I chi. So this scaling is allowed, and so therefore, so this is again the set. Yeah, anyway, allowed. And this scaling will give you, so this is also again give you U1 vector bundle over S2 sphere. Again, so this is called Bloch sphere. And then this, because vector in two entries is called qubit. And this S1 scaling will given in this, again, the hot vibration. S1 vibration, S2. Okay, again, the same confidence that appear to describe Dirac monopole appear even quantum mechanical system. But let's detour a little bit. But let's consider this two-entry vector and how we can interpret this Stern-Gerlach experiment. Okay. So the probability of the measurement is given by overlap of eigenvectors square. So that's the law of quantum mechanics. So namely, so first we consider the vector, so SG, Z, and we pick the Z plus. Okay, Z plus is given by Z plus given by this vector. So this is 1, 0 element is equal to 1, 0 element, 1, 0. And then next SGX, and we pick X plus. Okay, X plus. Sorry for my horrible handwriting. Let me erase because it's too unbearable to see. And in fact, this spin plus vector in X direction is indeed described by quantum mechanical rotation to the X-axis, which is given by here. So therefore, to get the how much percentage do you get the plus sign is indeed overlap between Z spin up and X spin up and take an inner product and take a square. Okay, let's do the computation. So remember, this is 1, 0. And then here, square root 1, 1. Okay, this is a multiplication. And then this vector multiplication is just given by pairing of this guy and the multiplication and multiplication. This 1 times 1 is equal to 1. 1 times 0 is equal to 0. So therefore, this will give you, this is equal to, is equal to 1 over square root 2. Okay? And then you need to take absolute value square, which is equal to 1/2. This is 50%. This means 50%. Let's do the same thing for -1, this one. So here, the spin minus. So therefore, you need to multiply minus sign here. But it doesn't matter because you just multiply 0. So therefore, the same. So therefore, what I did is this minus spin down X is square is equal to 1/2. Okay. So this means that here probability to measure the X minus is also 50%. Okay. Now we pick X plus and do the Z direction measurement. And how much percent do you get for spin plus is given by here. The same computation we give 1/2. Well, therefore, to get the Z plus here is 50%. Okay, it's a very simple multiplication, 2x2 matrix, 2-entry vector calculus, but that's how it works in quantum mechanics. Okay? So therefore, the memory that measure first experiment is erased after the measurement but on the X direction. Okay? And all those measurement is described by this simple linear algebra. And this normal commutativity of this observable Z, so namely, so as I mentioned, so these are eigenvector of this matrix. For instance, sigma Z eigenvalue are given by here. So Z plus and Z minus. So eigenvalue of this matrix, Pauli matrix, is X plus and X minus. Okay, and this non-commutativity of this spin observable will give you so-called uncertain perspectives again. So in quantum mechanics, so there is something ambiguity. So everything, as I mentioned, something like a probability. And then this probability of the is so quantum mechanical, so measurement has provide is a probability, and this probability concept probability leads you to so uncertainty relation. So this uncertainty is indeed defined by like this: delta A square is given by expectation value of the observable A square minus expectation value A itself and square. Okay? And then if you do the same applied, and then there's a so-called Robertson uncertainty relation, which is given by del A. A is observable, okay, and B is another observable. And this uncertainty of two observable is bounded by commutation relation between A and B. For instance, if you apply this Robertson uncertainty relation to this commutation relation, you get this kind of uncertainty relation, okay? Which can be easily derived derived by using the so-called using linear algebra. Okay, due to the time, I'm going to skip. The most famous, how to say, uncertainty principle in quantum mechanics is so-called position momentum uncertainty. In fact, in quantum mechanics world, position and momentum do not commute. So x and p commutation is given by I times the Planck constant. So x observable and p observable do not commute, which means that the del x times del p is bounded by h bar over 2. Okay? So this means that whatever particle you have, you cannot identify exactly the position of a particle and the momentum of a particle. So that's the meaning of this uncertainty principle, which is given by Heisenberg. This means what? If you try to identify where the particle is around here, so if the particle is around, particle is around here, okay, around here, okay, particle is around here. If you consider particle around here, you don't know the momentum very precisely, because I mean, if you identify the particle of the position, this is closely goes to 0. Then del P goes to infinity. Otherwise, this uncertainty principle will be violated. So this balance between del X and del P is indeed described as so-called Fourier transformation, which appear in classical mechanics. I explain for this Newton's law of the spring. And then this X and the relation between X and P is indeed is given by the so-called Fourier transformation. And then this uncertain principle is indeed given by this non-commutative X and P. Any question at this moment? So therefore, quantum mechanically, so the notion of the observable X means that you try to observe the position of the particle is X. And P is the position of the measurement of the momentum. That's observable. Any question at this moment? And
Professor, one still question.
go ahead.質問があるならどうぞ。
ありがとうございます。はい。数学科の遠藤真です。
はい。
いっぱいのスライド、前時期のスライドのに S2 と S1 の直積の話が出てきたと思うんですけど、
はい、はい。
S2 と S1 の直積の外形ってどういう風になるかって表現できたりしますか？
ちょっと質問が聞き取れない。質問を、繰り返すと、S2 と S1 の直積はどう見れるかですか？
そうだ。
外形ですか？
はい。
S2 と S1 の直積っていうのは、このまま、書けるんですけど、このサークルを書けるんですけど、この Okay. S2 no each point on S2 you have a circle and there is no twist in between. So I don't know how to draw, but direct product case it's very simple. I mean, just each point you have a circle and it's just no twist and yeah. Okay. For instance, okay. Well, I would say like this way. So if you have the S2 here, and you just take a two copy of and just consider some circle. Okay, interval, and just identify top and bottom. And identify top and bottom. Okay, then you will get the S1 cross S2. Do you understand what I mean? So this is you just consider S2 times interval 0, 1. And then you just identify top and bottom, you get the S2 times S1. Do you understand what I mean? I hope it answers the question. 質問に答えたでしょうか？
なんだろうな。多分質問の答えとしては、正しいのかもしれないですけど、多分自分が全然今、イメージできてなくて、
はい。
なんて言ったらいい？多分3次元多様体になるから、実際2次元平面に、なんかもう、なんて言ったらいいんだろう。
書くのはちょっと難しいんですけど、じゃあもうちょっと、じゃあ、これが多分一番いいと思う。これが S2 があって、それをちょっと、テューブラニボスって言うんですけど、なんて言うんですか、近状、周りのちょっと膨らませる、S2 をちょっと膨らませて、こうやって厚みを持たせるんですね。厚みをこうやって、厚みを持たせる。そして、内側の Q と外側の Q をアイデンティファイすると S1 クロス S2 になります。
アイデンティファイ
っていうのは、なんていうんですか。同一。ここのポイントとここのポイントは、こう、同一すると。くっつけちゃう。
だから、
と、S1 クロス S2 になります。まあ、ちょっと後で自分で考えてみてください。
各点で書く。
各点で、そうです。
難しいでしょ。だから、
まあ、ちょっと自分で考えてみてください。わ
かりました。ありがとうございます。
Any other questions? Okay, I think I'm very slow. I think I'm going to skip Schrödinger equation song. I'm just explaining that for this Schrödinger experiment, there's a wonderful book by J.J. Sakurai, and the introduction of this book will give you beautiful description of this Schrödinger explanation. So I just want to motivate to read this book. So now I have like 10 minutes left, 10 or 15 minutes left. So then I'm going to talk about special relativity. Special relativity is how to say established by Einstein, but around that time also Poincaré also considered the same similar theory. But in any case, in fact, this electromagnetism indeed do not enjoy Galilei transformation. Galilei transformation is essentially rotation and translation, which is invariant, which makes invariant under the space times distance. Space distance x2 minus x1. But t is time is the invariant, does not change. Okay? What Einstein proposed is that you just consider both t and x together as a coordinate. And then what we need to do is that the position of the space-time, these two distances do not change. So here you have a t and x, and t prime and x prime. They do not change. So these distances do not change. That is the proposal of Einstein. And then those transformation is called Lorentz transformation. And then the coordinate which simultaneously consider t and x as a coordinate is called Minkowski spacetime. So therefore, to preserve the 2 point length between 2 points in space-time, you have so-called, in addition to ordinary space-time rotation, you have so-called Lorentz boost. Okay, so you consider time and x, and which are mixed together by linear transformation like this way, and then which is given by something imaginary rotation, because I mean you have a cosine coshator and sinhator. Essentially, you have I times eta will give you just this one. Okay? So this is called the Lorentz boost, which give you the linear transformation time and space. For instance, this is one of the example of the Lorentz boost. And then, so here the new time coordinate is here, and the x coordinate here. So this coordinate is indeed frame of reference of the person which is the has a constant speed with the with respect to the person without speed. Okay, let's consider you are sitting on a chair and somebody with a constant speed, which is the half of the speed of light. Okay, speed of light. Okay, and then in that person, the coordinate of the time and the x are described by the relation like this in the Lorentz boost. What it means. So I just want to explain the phenomena of this Lorentz transformation by using one experiment. Let's consider the 300,000 kilometer. You have a tunnel. Is it the car with the speed of which is half of the speed of light, okay? Which is 150,000 kilometers per second. And then let's consider the situation. This car is just going through the tunnel, okay? Going through the tunnel, and we are kind of observing from the back and without speed. So therefore, our coordinate and time are space-time coordinate is this. But in terms of this person sitting inside a car, the coordinate it becomes x prime and t prime. Okay, so therefore, as you can see, so from outside a person, so this car is the half of speed of light, and the tunnel is 300,000. So therefore, in fact, when they enter when this car is enter the tunnel, it just position is here, and it just move our outside of tunnel out of tunnel. You get here. So therefore, of course, this time is 2 seconds here, and here is 300,000 kilometers. Okay. So therefore, outside of people, you measure this car will go throughout the tunnel at the 2 seconds. On the other hand, the person sitting in car the time is here. Okay. And 2 seconds for this person, the 2 seconds is indeed here. Not exactly equal to here. And if you use this Lorentz transformation, this is indeed 1.73 seconds. So this point is for the person sitting in this sitting in this car is in 1.73, which is less than 2 seconds. Okay? So somehow the notion of time will change, depending on the frame of reference in special relativity. Moreover, for the person sitting in this car, the meaning of length will change because for him, the space coordinate is x prime. So therefore, the intersection between the end of tunnel and the space coordinate is here. And if you use this Lorentz-Buss formula, in fact, it's a square root 3 of 1 times over 2 times 300,000 kilometers, which is 260,000 kilometers. So it's a shorter than the distance observed by from the outside people. Okay? So using special transformation, the time and the length, the notion become very relative to person. That's why it's called special relativity. Okay? And then I'm not going to explain detail because of the due to the time. So this the transformation that makes invariant under the length in space-time. So this length is called Lorentz transformation. And this Lorentz transformation can be described so-called SL2C Lie group. So the Lie group, so if you look at the very simple thing. So I introduced polymetrices. So this is polymetrices, and multiply this x, the space coordinate, and you have a 2x2 matrix. In addition to that, you just multiply the identity matrix and multiply t. You get this coordinate, this 2x2 matrix, and take a determinant. You get this t squared minus x squared minus y squared minus z squared, and we want to preserve this length. Okay? And to preserve this length is preserved by just multiplication, so-called complex 2x2 matrix, and take a determinant. That is indeed given Lorentz transformation. So this Lorentz transformation is indeed can be identified as to C, the group up to sign. Okay, so therefore this group theory is also involved in the special relativity. I wanted to explain the general relativity very detailed, but I don't think I have a time. But I will briefly explain. So the Einstein trying to generalize those so-called special relativity that to the general relativity, including gravity. So to describe a general relativity, you need to introduce so-called notion of curved space. So in curved space, let's consider two spheres and consider the so-called gray circle. Gray circle means like 赤道をちょっと回したような感じ。Let's consider some triangle bounded by this gray sphere. And let's consider their intersect normally. 45度のintersection. And in fact, this sphere is somehow round. It's not flat. And it's a metric. It's given by like this way. I think again, theta is here and phi is here. Phi is here. And then you can easily see that this triangle, triangle is indeed the area. So the area is the 4 pi. Suppose the unit radius is 1. It's 4 pi divided by 8. Because if you have a 8 copy of this triangle, it becomes entire sphere. Okay, so 4 pi over 8. Area is indeed pi over 2. And you might have noticed. So suppose you have a vector here, and just do the parallel transform. You just move right here, and you get this blue vector. Move along this gray circle, you get here. And move this vector along this gray circle, you get this vector. And this vector, you just move back to here. Okay? Return is this purple vector. Their difference is pi over 2. Okay? So this does not happen in the flat space. If you have the Euclidean space, you have a triangle here. And you start with some vector here, you just move here, You have here, and just move here. You have just parallel transform. You get here. You just come back here. You get the original vector. But this curve word, if you do the parallel transform, somehow original vector and the resultant return vector, there's a difference over pi over 2, which is given by area of the triangle. Moreover, we learn in Euclidean geometry alpha, beta, gamma. Sum of all the angle is pi. See, here it's pi over 2 plus pi over 2, 3 pi over 2, which is not equal to pi. Okay? In fact, alpha plus beta plus gamma minus pi is given by area of this triangle. So in curved space, so there's something more than what you learn in Euclidean geometry, which is flat. The same things due to the time, I'm not going to explain. So this sphere has a positive curvature K, positive curvature. But there's a negative curvature one can introduce, which use this so-called, again, Minkowski space, and they consider so-called hyperboloid, which is given here. And then consider the natural metric is given here, which has a negative curvature, which can be just mapped to this so-called Poincare disk by just do the so-called, it's called diffeomorphism, whatever you call it, or one-to-one map to this metric in disk. So this disk has a so-called metric like this. It's called Poincare disk. This has, even though this it looks just on a disk, the how to say shortest distance that this is called geodesic. It's called it's like it becomes like a sphere, like arc space like this. Okay, it's like a gray circle sphere, so it's called geodesic. Geodesic. This point, if you try to in the shortest distance, it become arc like this. If you try to how to say in this world, in this metric, this line is not it's longer than this line, this arc. Okay? This arc is shorter than this line. Okay? And then if you do the same thing for this Poincare disk, so this area of a triangle bounded by this geodesic is given by pi minus alpha plus beta plus gamma. It's very strange thing. As you might have seen, this is the picture drawn by Escher. Try to describe this Poincare disk. Anyway, so that anyway, to describe the notion of curved space, you have to use so-called Riemann geometry. So you have a metric, and the so-called you have a metric, and you have a geodesic equation, which is given by here, and this Christoffel symbol is given by first derivative of this metric, and then using this Christoffel symbol, you have a so-called Riemann curvature. So that will measure so-called the curvature of this curved space. For instance, this K or plus or minus is generalized notion, simpler version of this curvature R. In 1915, the Einstein so-called proposed so-called this equation. So left-hand side is this described as so-called curvature. So curvature, Riemann curvature, and the metric here. The right-hand side is called so-called energy momentum tensor. So this equation is derived by equivalence principle plus the general covariance, so-called. There are two assumptions, and you just from two assumptions he derived this equation. This essentially means that if you have some matter, so energy, that will or mass or whatever you have a very strong energy, the space term will be curved. Okay? The relation between energy and the curvature is given by this Einstein's equation. I just don't want, the purpose of my talk is to not explain this talk, but unfortunately, so from this equation, one can describe history of the universe, which is actually a wonderful book, two books by Stephen Hawking and Stephen Weinberg. These two books I highly recommend. And then rest of the talk, I just wanted to explain the black hole and so on, but I don't think I have a time. Anyway, so I will stop here in the summary and outlook. There's a relation between physics and mathematics, which is somehow very interesting for me. And then I want to motivate you why you have to learn this linear algebra or like whatever topology or Riemann geometry, even though a physics student, even for math student, you should keep eye on the physics phenomena or like quantum mechanics and so on. Behind these physics, there's interest in mathematics. I just wanted to explain that. To learn I just want to explain it. For physics or math student, I just want to suggest the students to go to library to explore a wide range of physics and math book. In fact, I just create a recommendation reading, which is available in my website. Indeed, this slide is also available on website. If you click this recommended reading, you can get this reading list. There is a wonderful magazine in Japan. Those books, you should regularly browse this magazine. And also nowadays there's online lectures, so YouTube and so on. So you should also you have AI is available. Okay, and I should stop here by leaving a very suggestive advice from the great mathematician. Thank you very much. I stop here.
どうもありがとうございました。本当に申し訳ない。ちょっと時間がもうちょっとなんで、でもなんか質問してみます？いいかな？多分いろいろと考えさせられるところがあって、物理学科の学生さんは、それなりに、数学と物理のことを考えてもらいたいし、数学科の学生さんは、それなりに、数学と物理の関係というふうなものをもう一度見直してみるのもいるかもしれないですよね。今まだ1年生ですからね。生物の学生さんとか、化学の学生さんはどうだったんだろう。ちょっと別の領域に入っちゃうかもしれないけれども、もしも余裕があるようだったらば、さっき示してくれた、アート、雑誌、本、あると思うので、ちょっと触れてみるのもいいのかもしれないですね。物理の学生さん何人ぐらいいるんでしたっけ？多分2年に同心学、2年の後期で相対論、で多分被るところもあるかもしれないけれども、いい決定になったんじゃないかなというふうに思います。もう一回、誰か質問しています。本当に最後なんですけど。よろしいかな？レポートの課題をさっきウェブクラスの方に載せておきましたので、あんまりレポートは考えないはずなので、ちょっと見て、レポートの回答の方をお願いします。いいかな？
僕のウェブサイトに行けば、調べてもらえば、ここをクリックすれば今日のスライドがあって、あとなんか、リーディングリストも一応載っけといたんで、これもアベラブルになってるんで、興味のある学生さんはどうぞ。
大変にウェルカムだと思いますので。いや、はい、じゃあ、長津先生、どうも本当ありがとうございました。長い時間。
いや、どうも。
やっぱりなんか疲れてんじゃねえかなと思いながら、最後の方は聞いてましたけれども、なかなかの熱戦で、印象にすごく残るセミナーだったと思います。また今後ともよろしくお願いします。機会があったら。
どうも。実は、僕、両親の実家がちょうど埼玉大学の、荒川の、反対側にあるんですね。で、 それで僕、埼玉大学、両親の実家に帰るときはいつも埼玉大学の図書館に行くんで、埼玉大学の図書館の数学科の図書館は特にいいんで、学生さんは、数学科の学生さんは特に数学科の図書館に行くとたくさんいい本があります。
覚えるんだ。ありがとう。覚えてると思う。はい、どうも
あと、
ごめんなさい。
大きな図書館もたくさん、数理科学とかの、コレクションがとてもいいんで、学生さんは見るといいと思います。
ありがとう。
ありがとうございます。
うんもし、質問がある人は、メールでも質問してくれてもいいし、ちょっと残って質問がある人は残っても、日本語で説明してもいいです。もし質問がある人は、ここで今解散して、ちょっと、はい。ちょっと今解散して、質問がある人は、個別に質問がある人は質問してもいいです。
うん。楽しかった。はい。じゃあ、このところで、次のあるところで、これで終わりにしたいと思います。どうもありがとうございました。
どうもどうも。
もう一度スイッチ消します。
永田先生。
はい。
上海では大変お世話になる。
いやいやいやいや、僕は何もしてないんで。いや一人学生さんが質問してくれたんですけど、他に学生さん質問したい人とかいますかね途中。
質問したいと言います。さっきね、質問してくれた学生さんにもう一回聞くことがありますかって言ったら、なんか自分としても、絞れてないみたいなことをおっしゃってて、今、クリームっていうのは。あ、整理するかと思いながら、大丈夫ですか皆さん。はい、毎度毎度すみません。シャイなものですね。では、上海ですか
何ですか
今、どちらにおられるんですか
今、上海にいます。上海に。
今、何時なんですか
学生さんで。
どうも。
今、何時なんですか
1時間前なんで1時半ですね。
はい。
いいです。ちょっと先ほど質問したものなんですけど、
はい。
そのイメージとしては、ちょっと見えるかな、
はい
この、ちょっと薄いかな。これちょっと、
はい
あれなんで見づらいと思うんですけど、この内側に球があって、
はい
そこにその
はい。
厚みを増していって、で
そうです、そうです。
ここの、なんていうか、この点と、この点をその同一視する。だから、
そうです、そうです。
つなげるっていう、
そうです
そのイメージとしてはそれで合ってるんです。
はい。はい。
なるほど。例えばその、さっきみたいな01の、
はい
いわゆるなんか直線区間みたいなやつだと、この
はい
端と端をこうつなげて円になるっていうのは、結構、
はい
イメージ自体はできるんですけど、これがその3次元、3次元って言っていいのかな ?3 次元の9と9の点を
はい。
同一視するっていう感覚って言ったらいいのかなイメージがいまいち浮かばなくて、
はい。
そうですね、これを、はいはい。
じゃあちょっとシェアにして、ちょっと待ってくださいね。
次は試験
次の試験あるんですか
次は試験じゃないので大丈夫です。
大丈夫ですかですね。えっと、
例えば、ここがスフィアがあって、で、そうですね。ここ厚みますと。でちょっとずれちゃったから。で、まあ、こっちの、ここが01ディレクションになってて、
はいはい。
で、端っこのこことここを同一するとサークルになるはずですよね。
はい。
で、うん。サークルになるはずで、それがどのポイントでもこうやってアイデンティファイすれば、ちょうどそういう風になってるはずです。すいません。
あ
いうん。こういう風にやってる。例えばこれ今、これをそうですね。で、まあまあもちろんこういう風になってるはずなんですけど、で、まあ、こことここをアイデンティファイ、こことここをアイデンティファイすると、ちょうど、あーここの部分のスフィアと、あと S1 ディレクションになってるっていう。で、例えば、今、
はい。
S2 を書いてないけど、ここを S1 にしちゃうと、S1 にしちゃうと、ちょうど S1 クロス S1 になるんで、ちょうどトーラスになるという。
うん。いわゆる、
うん、トーラスになる。そうですね。まあ S2 の場合だと、うん、ちょっと想像しづらいですけど、うん、今、ここの部分がこうなってて、ここの S1 の部分がここになってるんで、まあ、このやり方だとちょっと、うん、今、そうですなってるんですけど、まあ、それを、この S1 を S2 に変えてもできるという、そういうことですね。
だから、なんて言ったらいいんだろうね。Q があって、それをなんか、
はい。
ガシャラで切断したときには、円が出てくるじゃないですか。
はい。
その、なんて言ったらいい、円の周りに、表現がいまいち、うまい表現ができたけど、その円の、出てきた円の各点に対して、さらにその直積としたS1 が対応させれるから、だから、Q の切断面それぞれに対して、切断面無限にあると思うんですけど、その切断面それぞれに対してトーラスを作ることができて、それを、
うん。
Q に貼り合わせたというか、積み重ねたという。
ああ、それでもできますね。それでもできますね。あーっ
おー、
と、それでもできますね。そのやり方だと、この考え方だと、例えばこう S2 があって、えーっと、こういう、こういう風になってて、まあ、ここにプロジェクトすると。プロジェクトすると。こう。で、each S1 がこのポイントにプロジェクトすると。で、ここのポイントにトーラスがあると。で、あとこれに S1 をかけるんで、かける S1 なんで、まあ、each ポイントでここにトーラスがあるイメージですね。ここにトーラスがある。で、ここの端になると S1 だけ残る。ここの端になると S1 だけ残る。ここ、ノースポールとサウスポールは南極と北極がポイントになっちゃうんで S1 だけ残って、それ以外の場所では 他に S1 がここにあるんで、S1 クラス S1 でトーラスになるっていう。そんな感覚もできますね。言ってる意味わかります？
ちょっとだけ分かったような気がする。ような感じだから、
たと例えばこう、あれ。で、まあ、ここにプロジェクトすると。で、うん、ここに、どうなってんの？Good. So each point you have a circle. Yeah, for instance, here you have a circle, and then you have a times S1. So that if you multiply this, ここの S1 とここの S1 の直線かけるとトーラスになると。で、この S1 とこの S1 をかけるとトーラスになると。でもなんか、片一方のあと、片一方の、S1 はどんどんどんどん小さくなっていくから、どんどん小さくなっていくから、最終的に端ではこう、S1 になる。ドーナツの表面のここの S1 が潰れてなるっていう、そういう感じにも、そういうふうにもイメージできる。ということです。
いった状態を、極以外で切断すると、トーラスが出てくるけど、極で切断って言っていいけど、極で切断すると、S1、だから円が出てくるような図形ってことですか？
そうですね。
なるほど。でもなんか、なんとなくのイメージはつかみました。
まあ、
つかめてるかな？
いろいろ図を描いてイメージする練習をするといいと思います。1年生だな。
ありがとうございます。
いやいやいや。
頑張ります。
質問どうもありがとうございました。まあ、一人しか質問しても、もっと質問してほしかったんですけど。まあ、ちょっと、時間的にもちょっとあれだったかな。
すみません。じゃあ、改めてありがとうございました。
いやいやいやいや。じゃあ、これでおしまいにします？
はい。
じゃあ、ビデオがもし共有できるんなら、かどうかっていうのは後でちょっと E メールで教えていただけるとありがたいです。
いいよ。
いいですか？じゃあ、ということで。
違う。